Welcome to the third lecture video in our fourth class time series of lecture videos. In this lecture video, we're going to be embarking upon a discussion of paracyclic reactions, specifically electrocyclic reactions, because we have already looked at cycloadditions, which is a kind of paracyclic reaction. Geez, what are paracyclic reactions? Well, they are a reaction that exhibits a transition state with a cyclic array of pi electrons, and typically they're concerted. And so we've got cycloadditions, we've looked at that, a paracyclic reaction with two separate pi systems, and an example of that is the Diels-Alder reaction. And B, we've got these electrocyclic reactions. So that's a paracyclic reaction with a single conjugated pi system, so a single substrate, and it's doing weird things either under conditions of heat or light. So let's look at different types. Here we have a ring closing electrocyclic reaction. We've got a trine, and we're drawing, three double-headed arrows. We know electrons don't actually move, right? Like flowing in such a way. However, we have to use these symbols to sort of help us understand what a reaction is doing. We have some sort of transition state. There's some sort of concerted cyclic array of pi electrons. And lo and behold, if we followed that arrow pushing mechanism, we would end up with a cyclohexadiene. That's interesting. What's the change in enthalpy for this reaction? Well, what have we done? We've gone from 3 pi bonds to 2 pi bonds plus a single bond. So we broke a double bond and we added a single bond. Well, that's actually enthalpically favorable, right? We release energy. So that's good, right? Most reactions are enthalpically driven. For this reaction, we lose a pi bond, gain a sigma bond that is a single bond, right? A sigma bond is stronger than the pi component of a double bond, right? Which is why our reaction is exothermic. So let's look at another type as we continue this, discussion of notes. Here's a ring opening electrocyclic reaction. Here we've got cyclobutene, and lo and behold, we're heating it, and we follow these two double-headed arrows, and if we do that, wow, we get 1,3-butadiene. We've seen a lot of notes with this particular chemical as a reactant. That's kind of neat. What's the change in enthalpy? It is negative 9.7 kcals per mole, so this process is obviously exothermic. But what did we do? We exchanged a single bond for a pi bond. So for this reaction, we lost a sigma bond and we gained a pi bond. But wait a second, Dr. Wagner, didn't you tell me that a sigma bond was stronger than the double bond component of a double bond? Yes, that's true. But we also released the ring strain of a four-membered cyclobutene ring. And that helps drive this reaction, right? It adds to its exothermicity. And so, great. There's some interesting stereochemistry and stereochemical consequences that are associated with these paracyclic reactions. So, for example, let's take this 6 pi electron thermal electrocyclic reaction that we are heating. And when we convert this trine to a cyclohexadiene ring, we see something interesting. What do we see? We see that the methyl groups end up cis with respect to each other. And that's kind of interesting. What that means is when we went from trigonal planar on these terminal carbons of our trine system, our trine's pi system, to these tetrahedral carbons, these sp3 hybridized carbons. Well, when we did that, we formed a bond between them, and in fact, we had to start rotating this particular end of our trine in such a way that the methyl group would come up. and come out of the plane of the page and get this wedged bond, right? And if we rotated this end in that manner, so if I were an astronaut floating in the plane of the page looking at that as a propeller, it would seem to be rotating clockwise. Well, in order to get this other methyl group pointing up, this propeller on top would have to rotate counterclockwise. That's in the opposite direction, right? And so that's disrotatory, right? And of course, this little molecule, we can't just say, oh, the bottom side will rotate clockwise and the top side will rotate counterclockwise, right? It could have been the opposite case. If it were the opposite case and the bottom side rotated counterclockwise, then the top side would, in a relative sense, have to rotate clockwise, and both methyl groups would end up pointing down, but it would be the same molecule, right? You just have to flip it over. So yeah, wow. Either way, both propellers are rotating in opposite directions. We call that a disrotatory type of rotation. And this happens because of molecular orbital symmetry. I think we'll discuss that in the next lecture video. There's not enough time in this one to keep your attention held on this, but it's kind of interesting to see the reason why, right? We're all in college. I haven't been able to escape for more than 26 years. So we should be interested in the reason why, right? Wow, we take the same chemical, and this time we hit it with light. So we're doing a 6-pi electron photochemical electrocyclic reaction, and lo and behold, the methyl groups don't end up on the same side of our cyclohexadiene ring. They end up trans with respect to each other. And I don't only get this enantiomer, right, where both propellers rotated counterclockwise. Both propellers could have rotated clockwise, in which case I would get the non-superimposable mirror image of this cyclohexadiene, dimethyl cyclohexadiene product that's shown, right? At any rate, the important part of this particular reaction is understanding that these two propeller groups are rotating in a similar way, and we call that conrotatory, right? The methyl groups rotate in the same direction. And again, this is because of molecular symmetry. And I gave you some page numbers, I think it's 672 in the 5th edition. I'm sure there's a page number that explains it in the most current edition. But also, you know, this is the direct resulting product from both of these propellers rotating in a counterclockwise sense as I form a carbon-carbon single bond and my cyclohexadiene backbone framework, right? And that stops when this methyl group is pointing up, and we stop rotating once this methyl group gets his dash bond, right? I could have gone both clockwise in a clockwise sense, right? The molecule doesn't know, right? In which case I would get this stereoisomer. This is the enantiomer to the one that I've drawn up here. So both of these reactions are happening at the same time, right? And I get a racemic mixture, so 50-50. Like I said, I'm going to have to save the explanation for why our trienes rotate in a disrotatory sense under thermal conditions, but a conrotatory sense under photochemical conditions for the beginning of the next lecture video. I know you guys are all excited. You'll be held in suspense. You won't be able to wait to click on that next lecture video. I guess I'll see you soon.